Welcome to finding volume with disks. So again, the general idea here is if we rotate a region about, say, the x-axis, so for example, if we take this region here, which is just the area between the x-axis and some squiggly line above, between, say, A and B. If we rotate this region about the x-axis, right, we can break it into vertical slices, which might, if they are solid, form disks. So rotating our region again, we can break the region or the solid into vertical slices. And if they don't have any holes, they form cylindrical disks. So if they don't have any holes, the slices are cylindrical disks. I need to give myself just a little more space. Each disk, will have volume equal to essentially our pi r squared times delta x, whatever the width is, or pi times r of x squared times delta x. In this case, our radius is just the function value. So in this case, it would just be pi times f of x squared times delta x. As we let that delta x go to 0, then we essentially get that volume slice has dV, so a little sliver of volume, dV, is equal to pi times f of x squared dx. And therefore, our volume is just the integral from a to b of pi times f of x squared dx. So here, this is taking all of the possible cross sections, letting x run from a to b. So this is all possible vertical cross sections. between x equals a and x equals b. We can do a similar thing for rotation about the y-axis. So note, for rotation about the y-axis, then we get horizontal disks. And we get that our dv is going to be, we will have a pi times r squared, but this times r will be a function of y squared. And then we would do times dy, because if we have a horizontal disk, that height is in the y direction. And we get that our integral, we would go from a to b. Our volume is integral from a to b of pi times r y squared dy. So this is a nice trick that we have available to us if we can break our solid into just solid disks. So let's go ahead and take a look at example. Let's find the volume of the rotational solid formed by rotating the below shaded region about the x-axis. So the shaded region we are working with, we are looking at the region above the x-axis, below the line y equals x, between x equals 1 and x equals 2. So if we rotate this about the x-axis, then we will wind up getting a shape. We have our sort of trapezoidal region will be reflected over the x-axis. And then we just make all of those in rings, essentially. So it winds up being essentially a chunk of a cone missing its top on and the cone on its side. So we're running from 1 to 2 in terms of the x values. In this case, our radius is that vertical line running from the x-axis to the line y equals x. So our radius is just r of x is x minus 0. We have our dv, so our volumes are slice. We have dv should be pi times r of x squared times dx. Again, here we're looking at the cylinder slice. Where the cylinder radius just runs from the x-axis out to our line y equals x. So our dv is just pi times x squared dx. Our radius, again, x minus 0 is just x. So we have our dv. From here, we can jump to our volume. So for our volume, we are looking at our volume is just the integral from 1 to 2 of dv, well, from 1 to 2 of pi x squared dx. That we can go ahead and integrate. We are looking at pi over 3 times x cubed evaluated at 1 and 2. So this becomes pi over 3 times 2 cubed minus pi over 3 times 1 cubed. That's 8/3 pi minus 1/3 pi, otherwise known as 7/3 pi. So this is our total volume is 7/3 pi. This is a shape, since it is just a cone with the top chopped off, we could also have found this using just our knowledge of the volume of a cone. But this trick will allow us to find a volume of other shapes as well. So this is just basic finding volume by breaking our region into disks, or our solid into disks, and finding those individual and then integrating over all possible x values.